Good afternoon, guys. Okay, we will begin. Okay, so this is going to be our paper 4-2. Okay, May June 2021. Okay, so let's start now. Okay, so this is a 2 hours paper. Okay, I will go through everything again. Yeah. So you see here, okay, an aqueous solution of chromium 3. Okay, contains green complex ion. Okay, so we need to write the electronic configuration of an isolated gases of chromium 3 plus. So we know, yeah, when you look at the periodic table, okay, you will get that chromium, okay, is going to have, okay, the structure which is going to be argon, and you have 4s1 3d5. Okay, if you look at the periodic table, yes, okay, you will see chromium will have like something like AR. Okay, and then they have the 4s2 3d4, yeah, but they don't exist in this form. They will exist in this form because they want to be having all the d orbitals to be partially filled. Okay, so they will exist in that form. Okay, but now, okay, we want the isolated gaseous ion, which is 3 plus. Yeah, so when you remove the 3 electrons, okay, the 3 electrons are removed from the 4s orbital first. Yeah, so the one of the electron is going to be removed from here. Yeah, and the remaining 2 electrons are going to be removed from here. So you are going to get argon, okay, 4s0 3d3. So when you write down, okay, we need to write down from 1s2. Yeah, argon, okay, is going to be 2s2. Okay, that is 2 electron, 2p6. That's 8. That's already neon. Okay, 2 plus 8. So you have 3s2, okay, and 3p6. Now this is going to be argon. Now you continue, okay, which is you can actually put 4s0 3d3, okay, or you can actually just straight away ignore the 4s0 and just put 3d3 also correct. Yeah, so that is going to be the answer for this. Okay, and then they ask you to define the term complex ion. So how do we define complex ion? So complex ion is generally a molecule. Yeah, normally it's built from transition metal. So when the transition metal is going to be forming bonds, okay, with the ligands, okay, we call it as complex ion. So when we write down the definition, okay, it's better to write down it's a molecule that is formed, okay, by having a central metal ion, okay, or by having the metal or metal ion, okay, you are surrounded by one or more ligands that form dative bonding. Yeah, so this is going to be a good definition. So the points that we need to really focus on over here is going to be by having a dative bond, okay, to the central metal or the metal ion. Yeah, so you need to mention about dative bonding, okay, by the ligands. Okay, so these 2 points are very important. Yeah, so I'll continue further. Okay, for B, okay, this compound, okay, chromium with water ligands, they show similar chemical property as this, yeah, which is found in our syllabus. In our syllabus, okay, we will focus on the cobalt and copper. Yeah, so in this case, chromium, they say they show the similar chemical properties. So therefore, okay, whatever reactions that cobalt ions will undergo, yeah, they are going to follow the same, yeah, by the chromium. So the sample, okay, are reacted either, okay, in when we look at the ligand exchange, okay, we are going to focus on the OH minus, yeah. This one is under ligand exchange, and we know that, okay, the ammonia is also under ligand exchange. Okay, but this one, okay, is more towards the redox reaction. Later, we need to look at the data booklet. Okay, so here, okay, if you want to look at what will happen when OH, okay, is going to be reacting, okay, with this chromium, okay, the same. If let's say OH is reacting with cobalt, okay, what will happen? Okay, we are going to have, okay, cobalt, OH3, 3 ligands of OH will enter, and then you have the H2O, 3 of them will stay there. And then, okay, this one is going to be -3 because each of these ligand is going to be -1. So we know that this is going to be +3, okay. So this entire molecule, the complex, is going to be a neutral complex. Okay, and we know, okay, the cobalt complex, in this case, they are going to be a precipitate. okay, a solid precipitate. So in this case, we cannot just write down this, okay, we have to change this into Cr, okay, we have to change it into CrOH3 and then H2O and then 3. Okay, and then if you want to put the bracket also can, don't want to put the bracket also can, because they are neutral. Yeah, the type of reaction, since they are going to form a precipitate, a solid. So always remember, don't give simply the answer as ligand exchange. Okay, please actually think about some other reactions first. If let's say there is no other reaction, then only you mention ligand exchange or ligand substitution. So in this case, okay, we are going to call this as a precipitation reaction. Okay, so precipitation reaction. Okay, if you look at the marking key also, I will just double check with the marking key. Okay, this is going to be precipitation. So there is no answer, okay, in terms of where they give you answer in terms of ligand exchange over here. They will focus on something other than ligand exchange first. Yeah, so let's do this particular question first. Okay, with ammonia, what will happen? Okay, so if you react with ammonium, okay, if you react with cobalt, okay, you are going to get, okay, the cobalt, okay, all the water, okay, from there is going to be replaced, okay, by ammonia. Okay, so you are going to get 6. So if you have cobalt, okay, ammonia is going to be neutral, 0 charge, the ligand 0. So this one is going to follow 2+ over here if it is cobalt. Okay, but here we are going to change it into chromium. Chromium is 3+. So it's just write Cr, okay, and then NH3 and then 6. Okay, so we don't write 2+ over here. You need to write as 3+. Yeah, because chromium is 3+. Okay, water is 0. Yeah, so this reaction, okay, do remember this reaction, okay, is going to be producing aqueous. Yeah, so this is not a precipitation reaction. Yeah, so there is no other reaction that is suitable to show what is this. Then now you use the term ligand exchange, or you can use the term ligand substitution. I will keep it as ligand exchange. Okay, in the marking key, they put ligand substitution. Okay, it is accepted. Yeah, ligand exchange. Now, the next question is going to be when it is reacting with H2O2. Yeah, what will happen when they react with H2O2? Now, if you go and look at the data booklet, okay, if you look at there, okay, you will notice that you will get this information. Yeah, so I'll make it bigger. Okay, you will get that information which will help us, okay, to determine what is going to be produced. Yeah, so here, okay, when I look in the data booklet, okay, I noticed that, okay, H2O2, okay, they are going to give you this particular reaction. So I can rewrite this. Okay, H2O2 plus 2H plus 2 electron, they give you 2H2. That's going to be negative 1.77. Yeah, and then, okay, they are total, okay, they are total of three reactions involving the Cr3+. Yeah, so hold on. Okay, there are 3 reactions involving Cr3+. Okay, let me get that again. Okay, there are 3 reactions involving Cr3+. Okay, so here, okay, I've written here Cr3+ and so on. All the data are there. Okay, all the data are there. Okay, you can double check again. Okay, but I think this one also the number is missing. Yeah, but I think it's a negative value. Yeah, so negative value. You go and check the data booklet. Okay, but yeah, we want the reaction to react with H2O2. Yeah, H2O2 is a negative value. Yeah, so this reaction, okay, if you want to form a particular chromium species, is reacting with Cr3+. So the Cr3+, okay, must have a positive value, the E value, which is going to be more positive than negative 1.77. Yeah, then only, okay, we are going to have the H2O2 reacting. So if you look over here, okay, this is going to be a negative value. You can go and look at the data booklet. Yeah, and this is going to be a negative value. So if you compare, okay, these 2 values, okay, are going to be not suitable, okay, because okay, I want the CR3, yeah, if you follow this reaction, okay, this reaction, I want the CR3 plus, okay, to go to the, I want the CR2 plus, okay, hold on, okay, I would like to have, okay, the CR3 plus, okay, to react, yeah. So I want the CR3 plus to react, okay. In this case, okay, if you look at 1.33, okay, if you look at it, okay, you are going to have, okay, the reaction which is going to be, this is going to be, if I rewrite the equation, okay, I will have 2Cr3 plus, okay, plus with 7H2O, they are going to give you Cr2O7 2 minus plus 14H plus, okay, plus 6 electron, which is going to be a negative 1.33 if I convert that, yeah. So it means that, okay, if I get this particular reaction, okay, this particular reaction will happen, okay. Why? Okay, because this reaction, okay, is going to go to the, okay, going to change this particular reaction to this side, okay. And this particular reaction, negative 1.77, okay, is going to go, okay, and also react, okay, in this manner, yeah, this value. It all depends on this value, which is going to be this value, okay, 1.33, okay, should be bigger than negative 1.77. That's the entire idea, yeah. So cannot be, okay, cannot be negative value, okay, cannot be, even though negative value, okay, it should be, the value, okay, should be greater than or more positive than negative 1.77. So if you look at there, okay, what is the formula of the chromium species that is going to be formed? Okay, the formula is going to be, you are going to get Cr, okay, Cr2O7, okay, and 2 minus, okay, which is going to follow here. Okay, all these are taken from your data booklet. And the type of the reaction, okay, this is going to be involving, okay, you see that Cr3 plus is going to be positive 3, okay. You can calculate what is going to be the oxidation number over here, positive 3. This is going to be 2x minus 14, negative 2. 2x is going to be positive 12, x is going to be positive 6. So we are going to talk about oxidation reaction. You can write down the answer as oxidation because you are oxidizing Cr3 plus, or okay, you can write down as redox reaction. It's still okay, yeah. In this case, okay, H2O2 is behaving as an oxidizing agent. Okay, so normally H2O2, they tend to react, or they have tendency to react as an oxidizing agent or reducing agent. So in this case, they are going to have tendency to react as an oxidizing agent. Okay, so let's move on. Okay, now the next question over here is, okay, I will erase this part. Okay, they say that these two complexes, okay, they are complex of chromium 2 and they have different color, yeah. So whenever they have a transition complex, whenever they have different colored complex, yeah, we just have to, okay, normally when we ask why complex ion are going to be different color, okay, we need to find out, okay, we need to find out which one, okay, like for example, different color, okay, we need to tell specifically the d orbital splitting, okay, is going to have differently. The energy gap is going to be different. So on top of what we know, okay, on top of what we know, we just need to write down, okay, we need to write down what is going to happen, okay, what is going to happen whenever we have different ligand exchange, okay. So in this case, okay, okay, let me actually answer your question over there, okay. Okay, hold on. Okay, how do you know which one is reduced, which one is oxidized? Yeah. So how do I know, okay, which one is reduced and which one is oxidized? Okay, I will just give you a hint over here. If I have a particular reaction, okay, if I have A plus B, okay, to give you C, and then this value is 1.02. And then if I have another reaction, A plus D to give you E, and let's say this is going to be negative 0.47. Yeah. So we will always look at, okay, the more positive value, okay, the E value. So we know that this is going to go to the right, and the one that is negative is going to go to the left. Yeah. So do remember here is going to be always plus electron. Yeah, plus electron. So the one that is going to the right, okay, is going to be, we can say that, okay, this is going to be A, okay, is going to be plus with the electron, okay. So what is going to happen? So they are going to receive electron, gaining of electron. Okay, so in terms of gaining of electrons, so we can use the oil rig. Yeah, so reduction. We know that A is reduced. Yeah, and then we know that, okay, this particular compound is going to release the electron. Yeah, the E is releasing of electron. So I know that this one is going to be being oxidized. Okay, so that is how I know which one is oxidized, which one is reduced. Another way is to look at, okay, this is first, how do you get the arrow, yeah, left and right and so on. Okay, the second way is going to be you look at the oxidation number. Yeah, so you can confirm what will happen. Okay, so I think the question is more towards, okay, which one is oxidized? How do I know which one goes to the right, which one goes to the left? Yeah, so that one is answered over there. Okay, so this one, okay, the COH2O6, okay, for 1B, okay, let me check. Okay, for 1B, okay, doesn't COH2O6, okay, form, okay, okay, this one please check again. Yeah, please check again. Okay, okay, please check your textbook notes, Fredo. Yeah, so here, okay, so for B, isn't the first and third reaction both ligand exchange? Yes, okay, all of them. Yeah, to be exact, yeah, even this one is also ligand exchange. Okay, this is also going to be this one, no, yeah, so this one is also ligand exchange. Okay, as I told you, okay, we always, okay, use the one that is going to be we always try to look at the reaction, okay, determine whether they have other names for the reaction. Like if you are forming solid, then we say precipitation. If you have a reaction that acid plus base to give you salt and water, then we say acid-base reaction, something like that. Okay, let's say there is no other name, then we actually use the term ligand exchange. Yeah, hopefully that clarifies the doubt. Yeah, now, so why these color are different? Yeah, so you need to actually tell them, okay, each of them, okay, there will be d orbital splitting. Yeah, d orbital splitting will happen. Okay, but because, okay, this is going to be two different complexes, yeah, involving two different ligands. Okay, so d orbital splitting happens, okay, to generate, okay, to generate two non-degenerate orbitals. Yeah, because of your new syllabus, you need to write down all this. Okay, two non-degenerate orbitals. Okay, because of the presence of different ligands. Okay, because of different ligands. Okay, the energy gap, okay, between the two non-degenerate orbitals, I'm not going to write everything, okay, is different. Okay, it's different. Therefore, okay, when the electron becomes excited or promoted, okay, from lower degenerate orbitals to higher non-degenerate orbitals, okay, they are going to absorb, okay, different energy, okay, different energy from the frequency of wave, or different energy from the wavelength, okay, of visible light, and different complementary color is seen. Okay, different complementary color is in. So you just need to change, okay, the common marking key, okay, that we normally have, okay, and then we just try to adapt to this kind of situation, which is going to be the energy gap is very important. Yeah. Now, so the next part, okay, is going to be the structure is shown. Ethanoate ion, okay, is going to be acting as a ligand in this complex. Okay, the ethanoate ligand is shown as that. Yeah. So if you have this, okay, you are going to actually write down. Okay, they say that water and ethanoate ion behaves as different ligands in this complex. So you can see ethanoate ion, they are going to actually behave as bidentate ligand. Yeah. So you can see each of these ligand is going to form two dative bonds. Yeah. So it's bidentate, and then this water is going to be forming only one coordinate bond. Yeah. So dative bond. So you are going to have a monodentate. So if you answer this, okay, explain. So you explain based on this. Okay. Water, okay, you can just say water is going to be a monodentate ligand. Okay, they form, okay, one dative bond to the central CR atom. Okay, ethanoate ion, okay, on the other hand, is a bidentate ligand. Okay, they are going to form two dative bond to the central CR atom. Yeah. Okay, I mean 1B. Yeah, for 1B and so on, okay, I will answer later in the chat. Yeah, so we'll continue. Yeah. So now, yeah, deduce the coordination number of CR and the geometry around each of the CR atom in this structure. So now when you look at this geometry, yeah, this is going to be a special structure, yeah, where they are going to have, okay, you see that this is going to be one dative bond, okay, and you see one dative bond, okay, one dative bond, but do not forget there is another one more dative bond from the CR. Yeah. So if you look over there, each of these CR is receiving 6 dative bonds. Yeah. So it's going to be octahedral. Yeah. So I will answer the coordination number is 6 and geometry is going to be octahedral. They say that each CR atom. Yeah, so that is going to be the thing that you need to take note. Now, then they ask you what type of bond between CR and CR. You can see CR and CR. Okay, you can actually answer as they are forming dative bond, or they can form coordinate bond, or dative is a type of covalent bond. So if you write down covalent bond also, I think according to the marking key, they do write down covalent. Yeah, it's accepted. Okay, but I will write down the type of bond is going to be dative bond. Yeah. Now for E, okay, they say that, okay, this particular complex, okay, react with the acid to form Cr2+. Okay, so the Cr2+ ions react with oxygen under acidic condition. Okay, so we are going to we need to look at the data booklet. Okay, and then we need to get the information. Yeah, use the data booklet to answer the following question. Yeah, so I have actually taken the information from the data booklet. Okay, so if I make it bigger, okay, so here, okay, if I put it over here, okay, maybe I'll put it here first. Now, okay, when I look at this, when they say that they are reacting with oxygen under acidic condition, okay, I first, okay, look at the equation, okay, that inside the data booklet, okay, which gives you H plus and oxygen. Yeah. So when I look at over there, okay, I notice that, okay, I do have this particular equation, okay, which is going to be, I'm going to highlight, okay, this is the particular reaction that I have, yeah, 0.68. And then, okay, when I look at the reaction, okay, for the Cr3+, okay, for Cr2+ and involving Cr3+, okay, I get this particular reaction, okay, which is going to be, okay, I will highlight also, okay, this particular reaction. Okay, but okay, when I get that value, okay, from the data booklet, I didn't get it in that way. Okay, I get it in Cr3 plus electron. Okay, I get it as negative 0.41. Yeah. So, but okay, they say that okay, Cr2 plus is reacting. So what you need to do, you need to take this reaction, okay, and you need to turn it around. Yeah, so I turn it around and it became 0.41. Okay, and then I have 0.68 over here. Okay, when I try to join these two equations together, yeah, I need to cancel the electron. Okay, when I cancel the electron, okay, I need to times this by 2. Yeah, but whenever you times this by 2, don't go and times this by 2. Yeah, this one, the E value will only change in terms of positive and negative, but we do not times it by 2. That value normally we times for the enthalpy or energy change calculation. Yeah, for this one, no. So when you add this, okay, when you add this, you are going to get 1.09. Yeah, 1.09. Okay. Okay, that is going to be the answer that you can give. Yeah, but okay, do remember, okay, there is going to be another type of equation, okay, that you can actually use. Okay, so that's why, okay, I will use this particular equation, okay, involving the O2 and this, okay, which is going to give me, okay, positive 1.09. Yeah, so there is going to be another answer also. You can also check, okay, because it involves two types of equation. Yeah, the equation that I am going to use, okay, is going to be the equation that involves, okay, the one that gives me H2O2. Yeah, there is another type of equation that you can use, okay, which is going to be involving, okay, the O2 and H plus, okay, which is going to give you H2O. Yeah, so if you do that, okay, you are going to get this as the reaction. And when you calculate, okay, the value that you're going to get after you calculate is 1.64. Yeah, but I am going to use this particular reaction which I showed to you just now, and when I calculate, okay, I am going to get the 1.09. Yeah, so there are two answers that you can choose and give. Okay, so the one that I'm going to use is this particular answer, okay, which is that's why I put it over here. Okay, under this condition, yeah, this is the ionic equation that I'm going to use. Okay, so this is the reaction that I'm going to use. Okay, and then the E value, okay, is going to be, I'm going to use it as plus 1.09. Okay, so I will erase all this first. Okay, there are two ways. Okay, it means when you look at the data booklet, there are two equations, okay, for the oxygen and the H plus that you can use, yeah, for this reaction. Yeah, so I'll move on. Okay, for number 2, okay, state and explain the trend observed in the thermal stability of group 2 nitrates. Yeah, so when you look at group 2 nitrates, okay, going down group 2 nitrates, okay, we know that group 2, okay, we know that the ionic radius is going to become bigger and bigger. Okay, as the ionic radius, okay, the cation, yeah, when it becomes bigger and bigger, what we can say, the polarizing power is going to decrease, yeah, because of the charge density. Yeah, charge density is going to be less, so the polarizing power decreases. So in that case, they cannot distort the electron cloud of the anion, okay, and therefore the bond between nitrogen and oxygen in the nitrate, okay, become less weakened. Okay, therefore, okay, you can say the thermal stability is going to increase. Yeah, it means that they are going to be stronger to heat. Yeah, so if you answer that, okay, I have actually answered before. Okay, I'll just make it bigger and we'll go through. Okay, what is important over here. So here, okay, they say that the thermal stability increases down the group. Yeah, so that's going to be 1 mark. You need to mention about the ionic radius of the group 2 cation. So the ionic radius is going to increase. So very important to mention about that. Okay, which this is going to decrease the polarizing power of the cation. Okay, therefore less distortion towards the electron cloud of the anion. Okay, and the bond between NO in nitrates are less weakened. Okay, and you need more energy to break them. Yeah, so that is going to be what you need to do, remember. Yeah, so you need to write down that, yeah, to get the 3 marks. Okay, so the next question, okay, they say that lead nitrate, okay, it's going to decompose, okay, on heating in similar manner to group 2 nitrates. So you just need to use the normal way, yeah, which is going to be PbNO3. Okay, when they decompose, okay, they are going to give you PbO plus, okay, NO2 plus oxygen. So you just need to balance them up, yeah. So when you balance, okay, here, okay, when I balance, okay, I need, okay, if I erase this, I think I'll just do here. Okay, let's say now if I put PbNO3, yeah. So if I try to balance this up, okay, so this one, okay, you just need to put 2 nitrogen over here because 2, yeah. And then if I look at the oxygen, there should be 6 on the left. So if I look over here, they are going to be 4, 5, and then I have 7. So I need to put half over here. And I don't want half. I need to times everything by 2, yeah. So I just put 2 here, okay, 2 here, and then this is 4, then this is going to be 1. So that's why, okay, when you write down, okay, you write down, okay, here 2, okay, and then here is 2, this is 4, and that is 1, yeah. So this one, okay, you can write down, okay, solid, okay, this is solid, okay, this is gas, okay, this is gas, okay, that. Now suggest, okay, the ease of decomposition, okay, in comparison to barium nitrate. And then they say that, okay, you need to refer to the data booklet. So in this case, again, okay, when you look into the decomposition, okay, you need to look into the ionic radius again, yeah. So this one is not in Pb2 plus, it's not under group 2, yeah. So you need to find out what is the cation radius, yeah. So the Pb2 plus radius, okay, from the data booklet. So if you get from if you go and get it from the data booklet, you will notice that Pb2 plus is 0.12, yeah. Ba2 plus is 1.35. You will get it from the data booklet. So we know that, okay, Pb2 plus is smaller, yeah. When Pb2 plus is smaller, okay, we know that Pb2 plus has more polarizing power. Okay, so if you have more polarizing power, so you see when I answer, yeah, so I say that Pb2 plus is going to be smaller ionic radius. I mentioned the value. And then compared to Ba2 plus, okay, then I say the Pb2 plus because having stronger polarizing power, or you can say they have larger charge density, yeah. So the charge is the same, okay, charge is 2 plus, okay, so in this case, they are smaller, okay. So why charge density, if you ask me, then it's actually you need to go and check again, charge divided by radius, yeah. So this one, okay, charge density is larger, so therefore, okay, they can distort the electron cloud of NO3 nitrate ions, okay, and weaken the bond between NO, okay. Therefore, PbNO3, yeah, lead to nitrate, they can be decomposed easily compared to barium nitrate. Yeah, so that is going to be giving you the 1 mark. Yeah. So the next one, okay, barium ethane diovate decomposes on heating to produce barium oxide and a mixture of 2 different gases. So if you have this reaction, yeah, this one I think a lot of students will get confused. Yeah, ethane diovate, yeah, when you decompose ethane diovate, yeah, they are going to give you whether the 2 gases, maybe students will think carbon dioxide or maybe oxygen, yeah. So this one is wrong, yeah, you are not going to get oxygen, okay, because ethane diovate, yeah, there are only limited reactions in chemistry that will give you oxygen gas, yeah. So like for example, decomposition of nitrate, yeah. So in this case, you can have carbon dioxide, okay. The another one, yeah, another gas is going to be CO gas, okay, carbon monoxide gas. So you can actually try to balance up using that reaction, yeah. So that is going to be how you balance the reaction. So okay, if you look at here, okay, I think there is they give you, okay, the reaction with oxygen, okay, over here, okay, in the marking key, okay, but okay, it will give you carbon monoxide, not carbon dioxide. Yeah, so this one maybe might, okay, be confusing for some. Yeah, so I will suggest, okay, please remember, okay, there are quite limited reactions, okay, involving reactions that gives you oxygen. So I would suggest to remember Ba, okay, C2O4, okay, when they decompose, they give you barium oxide. They have given you that, okay, and then give you CO2, and then they give you CO. Yeah, so just try to balance this up. There are 2 carbon already done, okay, and then there are 4 oxygen done. Barium is there, so it's already balanced. Yeah, so if you want to write down, okay, the state, up to you. You write down, okay, but they already mentioned these 2 are gases, so just give it like that. Yeah. So the next question, okay, this one is going to be involving calculations. Yeah. So an impure, okay, B8, this compound, okay, they have mass of 0.5 gram. So added to this, okay, so first you find out what is the number of moles of MnO4 minus first. Yeah, so they are going to be titrated. Yeah, they are going to be added in excess. Yeah, so find out the initial, okay, initial number of moles. Okay, you can get it from 50, you times with 0.02, okay, divide by 1000, you will get the number of moles. Okay, the initial number of moles, if you count, is going to be, you will get 1 times 10 negative 3 moles. Okay, you will get that. Okay, once you have that, okay, it is reacting. Yeah, and then for the resulting solution, yeah, containing unreacted MnO4 minus. So it means not all of this, okay, reacted. Okay, there are certain portion that is not reacted, so they titrate it with Fe2 plus. Okay, they titrate with Fe2 plus. So let's actually find out what is the amount of Fe2 plus that is reacting with MnO4 minus. Yeah, so number of moles of Fe2 plus. Okay, same way. Okay, you use the 30.4, okay, times 0.05 divided by 1000. Okay, and you will get, okay, 1.52 times 10 negative 3. Yeah, if possible, yeah, please use the more significant figures. Yeah, so this one is the value that I have. Yeah, but normally, okay, when you calculate, please keep it to 5 significant figures. Yeah, it's better. Yeah, now once you have this, okay, number of moles of Fe3 2 plus, okay, this is the number of moles, and then you need to calculate the percentage by mass. So in now what we need to do is you need to write down equations. Yeah, so here the Fe2 plus, okay, is reacting with this equation. So let's actually try to write a balanced equation, okay, involving these 2. Yeah, so I will erase this one first. Okay, so you see that, okay, they have 5 electrons here. So in order, okay, to get a proper equation, yeah, so you need to cancel the 5 electron. Yeah, so you times everything by 5. So you will get, okay, when you balance that, okay, you will get this particular equation. Okay, so I will rewrite again for you. So MnO4 minus, okay, plus 8H plus, okay, plus 5 Fe2 plus, they are going to give you Mn2 plus 4H2O plus 5 Fe3 plus. Okay, so the number of moles, okay, that we know that Fe2 plus reacted just now is 1.52 times 10 negative 3. Yeah, so this one. So I can find out, okay, what is this number of moles. Yeah, so it's going to be divided by 5. Okay, so 1.52 times 10 negative 3 divided by 5. Okay, you will get, okay, the value is going to be 3.04 times 10 negative 4. If better, more significant figures. Yeah, so once you get this, okay, we know that this is going to be the number of moles, okay, that is in that didn't react. Yeah, so we can find out number of moles of MnO4 that reacted. Yeah, so you can actually find the difference, okay, between these 2. Yeah, so you can calculate that. So number of the MnO4, okay, that reacted earlier, okay, is going to be, you can just use that value, okay, and MnO4 minus reacted, okay, equals to 1 times 10 negative 3, you minus with 3.04 times 10 negative 4. Okay, and you will get, okay, the value is going to be 6.96 times 10 negative 4, okay, moles. Okay, once I get that, okay, it's not done yet, okay, because we know that it is reacting between this and this. Yeah, so now we need to do the same thing again, okay, which is going to be this one. You need to times everything by 5, okay, to get 10 electron. Okay, this one you need to times everything by 2, okay, to get 10 electrons, so that we can get an overall equation. Okay, the overall equation, okay, if I calculate, okay, if I write down, okay, maybe, okay, I already wrote down here, okay, the overall reaction, okay, I'll just make it bigger. Okay, if you calculate, okay, if I join these two equations together, I am going to get this particular equation, okay, and then, okay, I know just now MnO4, the one that I calculated, that one reacted 6.96 times 10 negative 4, okay, that is going to be represented by this, okay. So 2 moles of MnO4 minus. Yeah. So what we need to do is to calculate the amount of C2O4. Yeah. So this is representing for 2 moles. I want for 5 moles. So what I need to do, this value I divided by 2 to get 1 mole. Then I want 5. I times by 5. I find out that this is going to be 1.74 times 10 negative 3. Yeah, moles. Okay, and since, okay, I know that, okay, this compound, okay, which is this compound, okay, they are going to give you 1 mole of this, is going to give you 1 mole of this and 1 mole of this. Okay, so if I have this as my number of moles, okay, what is this number of moles? Still the same. Okay, so I can calculate, okay, what is the mass, okay, by using the formula number of moles equals to mass over mr. Okay, so the number of moles, okay, you times with the mr. Okay, the mr is given. Okay, you no need to look at the periodic table, 225.3. Okay, so you use the mr value and you will get, okay, the number, the mass of BaC2O4 as 0.39. Now, once you get the 0.39, okay, you divide that with 0.5 over here and times 100%. Yeah. In this case, okay, because I didn't use a proper significant figure, yeah, I get 78.0. Yeah. If you use a more significant figures, okay, you will get the one that is exactly what is required in your in the marking key, okay, which is going to be 78.4. Yeah, so that's the importance, okay, of using, okay, more significant figures. Yeah, so you only simplify to 3 significant figures towards the end. Yeah, so that is very important. So this one, the answer, okay, I will put it at 78.0%. Yeah, but the answer is 78.4 because, okay, along the way when I calculate, it's all in simplified version. Yeah, so you need to make sure you have more significant figures. Yeah, then you simplify towards the end. Yeah. Next question, okay, barium hydroxide completely dissociated in aqueous solution. So we want to calculate the pH. So the pH can be calculated. Okay, if you know barium hydroxide, okay, they can actually be written as Ba 2 plus and 2OH minus. Okay, so if you have 0.12 over here, okay, so we know that this is going to be double, so 0.24. Yeah, double the amount. So we want to calculate pH. Okay, you can actually calculate using this formula. POH equals to negative log concentration of OH minus. This is similar with pH formula. Okay, once you do that, yeah, you are going to get the value, which is going to be negative log 0.24. You get 0.62. Yeah, and we know that since this is going to be aqueous solution, yeah, so the formula for that is going to be Kw equals to Kw, okay, the pKw is going to be pH plus POH, and pKw, okay, you should know it's going to be 14. Okay, 14 equals to pH plus POH. You can solve this using this formula. Okay, which is going to be, if you want to find pH, it's going to be 14 minus pH, which is going to be minus POH, which is going to be 0.62, and you will get the pH as 13, okay, In this case, 13.38. Okay, you simplify. Okay, 13.4. Yeah, three significant figures. Okay, that is how you calculate for this. Yeah, quite simple. Yeah. Next, okay, define the term standard electrode potential. Yeah, this one every year they will ask this kind of question. Yeah, standard electrode potential. Okay, is different than the previous. I think the paper 4.1 they actually asked about standard E value, yeah, E cell, yeah, they ask about standard cell potential, yeah. So that is different. Standard electrode potential is going to be in comparison to the hydrogen half cell. So how do you define? You define the voltage of the half cell connected to half cell of that electrode connected to a standard hydrogen half cell. Okay, and the condition must be standard. So which is going to be 1 mole per dm cube. Okay, and then the pressure must be 101 kilopascal. Okay, temperature 298. So all this must be there. Okay, so the definition, yeah, is going to be, I will just enlarge this. Okay, is the voltage, okay, of a half cell, okay, connected, okay, to the standard hydrogen half cell, okay, at the concentration of 1 mole per dm cube, okay, and the standard condition. So you write down 101 kilopascal, 298 Kelvin. Yeah. Now the next question, you have a 3 redox system over here. Yeah, and then the ligand is represented by En. Yeah, so basically you have all this system over here. So what I did over here, the first thing is I put down, okay, this RUEN. Okay, so you see RUEN. So this system is going to be C. So I put down this as C for myself. Okay, and then with ammonia, so I put this as B. Okay, with water, I put that as A. Okay, and with En, so I put it as C. Yeah. From here, okay, what information that I get? Okay, I see the negative terminal. Negative terminal is where the electron coming out. Yeah. So I will draw the electron is coming out from here. Yeah. Then you see here negative terminal, the electron is coming out over here. Okay, this is going to be very important, okay, to predict, yeah, the E cell, which one most negative or least negative over here. Now from here, okay, what I can do over here is now I compare one by one. Okay, let's compare B and C. Yeah, B and C. So if I compare B and C, if let's say this is the one that is releasing the electron, okay, it means this one, the C is receiving the electron. Yeah, so it means that, okay, this C, which is receiving the electron, okay, should be more positive, the E value, yeah, the standard reduction potential should be more positive than B. If I put it in terms of numbers, okay, between B and C, yeah, in terms of numbers, okay, let's say I give a value, okay, of 5, okay, for B, okay, and then this is going to be 10, okay, for C. So if it is 10, okay, that means that the more positive value, okay, 10, is going to receive the electron. So it is going to go to the right. The C equation is going to go to the right. Okay, the one that is going to be less, okay, value over here, they are going to have tendency to go to the left. Yeah, so you can see it is releasing electron. Yeah, so that actually matches, yeah, with what we want, yeah, which is going to be releasing the electron. So I'm just going to use these two numbers later. Yeah, now if you look the same thing over here between A and C, yeah, we notice that A is the one that is receiving the electron and C is the one that is going to be losing the electron. So you see between A and C, so let me erase this. Okay, between A and C, okay, I know that, okay, A is receiving electrons. So it means in order to receive the electron, C must be receiving the electron. So they are going to be, A must be receiving the electron. A must be receiving the electron. A is supposed to go to the right, okay, receiving the electron. And C should be the other way around. They're supposed to be going here. So if I look at the number, okay, this value is supposed to be greater than C value. Okay, if I gave the value here as 10, okay, maybe here I can give 25, 30, or 15. Yeah, so I'll give 15. Okay, 15 is going to be greater than 10, so it's going to go to the right. So when it goes to the right, okay, I can know that, okay, now if I want to compare using the number over here, okay, I know that the more, okay, the E value, okay, the one that is going to have the bigger value is going to be something that is going to be more positive, yeah, more positive, okay, compared to the rest. So the one that is most positive is 15, yeah, which is going to be A. So I will write down this is A. Okay, the one that is smallest or the most negative, yeah, is going to be 5, which is going to be B. So I'll just put B. The one in the middle is going to be C. So I get this answer. Yeah, this is how you solve this particular question. Yeah. Now the next part, okay, you are going to have, okay, this complex, okay, showing stereoisomerism. Ligand is a bidentate ligand, and we need to draw, okay, the three-dimensional diagram. So every single time when I draw this, okay, I will always draw something related to this, yeah. And then, okay, when I want to draw the ligand, yeah, so I'll put this one N, yeah, and then it's going to join, okay, with the you are going to join the top, yeah, the top, okay, it's going to join with the N over here. Okay, so I'm going to draw like that. Yeah, so I will draw something like this. Okay, hold on. So this one I just put like this. Okay, now I will join this from the bottom, okay, to this particular N over here. Okay, so I will draw like this, and left with this N and this N. Okay, so I'll put something like this. Okay, the final part that you need to draw is going to be to show that it's coming out from the paper. So just draw like this, and then to show that they are behind, so you draw something like this, you draw something like this. Okay, so this is going to be one of the isomer. Then the mirror image, yeah, the mirror image of that, okay, you're supposed to draw on the right. Okay, so here, okay, maybe I'll just enlarge over here. Okay, so this is going to be the mirror image. Okay, you can compare. Okay, so you are going to get, okay, let's make it smaller. Yeah. Okay. You are going to get this structure, okay, which is the mirror image. Okay, so the type of stereoisomerism that we are going to talk over here is going to be the optical isomerism. Yeah, so optical isomerism. Now the next part, okay, they say that, okay, this is involving electrochemical cell, okay, this and this. Okay, in order to do this, okay, you need to look at the data booklet. Okay, so the information from the data booklet that I have over here, okay, I am going to use that information. Okay, so maybe I'll put it here first. Okay, when I look at that information in the reduction form, yeah, I will get Br2 plus 2 electron to give me 2 Br minus. That's going to be positive 1.07. Okay, and if I have the Ag plus, okay, I will get this one in form of Ag, which is 0.80. Yeah. Now, using this information, yeah, what do I get? Yeah. As I told you, the one that is more positive, they will move to the right. Yeah. So 1.07 is more positive than 0.8. So they are going to move to the right. Okay, and the one that is going to be moving to the left is this one. Yeah, so when I write down, okay, deduce the direction of electron flow, you can see Ag is going to give out electron. Yeah, so if I want to deduce the direction of electron flow, now itself I can give you, okay, which is going to be the electron flow is going to be from Ag plus Ag half cell, okay, to Br2 and Br minus half cell. Yeah, so this one you know. And then now if I want to calculate the E value, then you need to rearrange again. Yeah, Br2 plus 2 electron to give you 2 Br. Okay, and then this one is going to the left. So you write down Ag, okay, is going to give you Ag plus electron. So this one is 1.07, no change, but this one is negative 0.80. And do remember, if I want to eliminate the electron, yeah, I need to times everything by 2 over here. But I do not times this by 2. Yeah, E value, you don't times by 2. So you just need to find, okay, you just need to add these two together to get the E cell. Okay, when you add that value, okay, you are going to get, okay, the value of E is going to be, okay, positive 0.27. Yeah, that's going to be the value. Okay, now the next part, okay, is going to be, okay, let me erase first. Okay, the next part is going to be, you are going to add, okay, you are going to add water into the half cell of Ag plus. Yeah, so Ag plus, do remember, okay, Ag plus electron to give you Ag in the beginning is 0.80. Yeah, so now, okay, what is going to happen when you add water? Yeah, water is going to make the concentration of Ag plus to become less. Okay, when the concentration becomes less, okay, the position of the equilibrium will be shifted to the left. Okay, to remove or to increase the concentration of Ag plus. When it goes to the left, okay, what happens? This particular value, okay, is going to become less than 0.80. Yeah, less than 0.80. Let's give a value. Yeah, so let's say from 0.80 becomes 0.50, for example. Yeah, so just now, okay, when I calculate, okay, I calculated the value, okay, by putting 1.07, and this one is negative 0.80. Yeah, so now, okay, maybe I'm going to change this into negative 0.50. So what will happen? Yeah, when I do that, okay, I am going to have, okay, 0.57, positive 0.57 volt, okay, in comparison to 0.27 volt just now. Yeah, so now you can say that, okay, the E value, okay, is going to become more positive. And when you explain, okay, you just need to explain, okay, the concentration of Ag plus decreases. Okay, therefore, okay, the position of the equilibrium, okay, shifted to the left. Okay, and when they shift to the left, okay, you are going to get the E value, okay, it's going to become less, okay, than 0.80. Okay, so when I calculate the E cell value, okay, the E cell value now is going to become more positive. Okay, so you just write down, they become more positive. So these are the things that you need to include when you give your answer. Yeah, so no need to say 0.5. Yeah, so we already tell, okay, as long you can tell this value is going to become less than 0.80 is good enough already. Yeah, so next question, next part, okay, you see here, okay, silver bromide, okay, dissolves in aqueous solution S2O3 to form the complex ion. Okay, the ion acts as monodentate ligand. Yeah, so when they ask you, normally they ask you define bidentate, define monodentate. In this case, they ask you to define in general ligand. Okay, what is ligand? It's a species, okay, that can form, okay, or that has lone pair of electron, okay, and lone pair of electron that can form, okay, dative bond, okay, dative bond to the metal or metal ion. Okay, so make sure you write down dative bond and metal or metal ion. Yeah, that is important. And then they ask you to write the equilibrium constant for equilibrium 1. Yeah, the important thing that you need to know is, yeah, this is solid, so we do not include the solid in our Kc value. So it's going to be this and this product, yeah, divide by the reactant, and this is 2, so this one should be to the power of 2. Yeah, so I have written earlier, okay, so I'll just enlarge and I put it over here. Yeah, so you can check as well. Okay, this is the product, Okay, so product, and then this is going to be to the power of 2 because of this 2. Yeah, that is going to be Kc value. And then now some additional data are given, okay, about the dissolution of AgBr in S2O3 2 minus. Okay, the first data that is given is going to be Ksp, and we know the Ksp, okay, is going to be you can write down, okay, Ksp is going to be AgBr, okay, solid to give you Ag plus, and then Br minus. Okay, so this one, if I write down in solubility product, okay, the term, okay, is going to be like this. This is Ksp. Okay, so you write down that, okay, I will not include AgBr solid over there in my Ksp. And then, okay, the another part is going to be the K step, yeah, stability constant. Okay, this stability constant is formed, okay, because of the presence of Ag plus, yeah. So Ag plus is going to react with this S2O3, okay, because these are the ligands, okay. This is the metal ion, and you are going to get the complex, okay. That's the equation, okay, that's the equation. So when I write down over here, okay, generally I am not going to use AgBr over here. Yeah, so I'm not going to use AgBr. I'm going to use Ag plus. Yeah, from the, because AgBr is solid. Yeah, so we want the Ag plus in aqueous. Okay, the one that after you have the solubility product, okay, that Ag plus is the one that is going to react with the ligand, and then they are going to tell us whether the complex is going to be stable or not. That is the reason why we use K step, yeah, stability constant. So once you get this, okay, I will write down the K step as in this form, yeah. So this is the expression, okay, of K step, okay, which is going to be just normal, yeah. So everything is written over there. So if I want to find out, use your answer here, Kc, yeah, and then I use all these value, okay, and then I need to calculate the Kc, yeah. If I want to calculate the Kc, okay, what do I need to do, yeah? So in this case, I know that, okay, my Ksp, okay, Ksp is Ag plus, and then, okay, it's going to be Br minus. Okay, that's my Ksp. If I can get, okay, I need to actually derive, okay, a way how to join these two together to get this, yeah. So I have the Br minus at the top, okay. How to get this particular value at the top, okay, when I see, yeah, this is at the top. And then when I times these two, yeah, so if I try to times these two, okay, which is going to be my Ksp, okay, I times with K step, okay, which is going to be, if I times, okay, let me copy this. Okay, if I put it here, okay, I'll make it slightly bigger. Okay, if I do that, okay, what will happen? Okay, I can cancel the Ag plus, and I cancel the Ag plus, and I will get Br minus times this divided by this particular value, which is the same as my Kc. So I know that Kc equals to Ksp times K step. This one you need to figure out on your own. Yes, normally it's directly times, or you need to actually invert this, maybe Ksp times 1 over K step and something like that. Okay, you need to figure out. Okay, and then you can calculate. So Ksp, okay, is going to be 5.4 times 10 negative 13. So you times with the K step, which is going to be 2.9 times 10 13. Okay, and you will get the Kc value. Okay, the Kc value, if you calculate, okay, you are going to get, okay, I think I'll just use this value here. Okay, the Kc value, okay, if you calculate, it's 15.7. Okay, if you get this, okay, 15.7, and the unit, yeah. So unit, you can always check over here, okay, to the power of 1 to the power of 1 divided to the power of 2. So anything to the power of 2, concentration to the power of 2 divided to concentration to the power of 2, cancel, cancel. So there is no unit, okay, no unit. So this one you can do it on your own, yeah. Now, okay, actually it's not a known equation. Yeah, it's not a known equation. So Kc is not always K step times Ksp. You need to figure out. Yeah, so it means that you need to like solve a puzzle. Yeah, this one is going to be this equation, this is going to be this equation. How do I relate to, if I can get something related to that? So I need to play around. Yeah, so that is how you get the value. Yeah, sometimes okay, you will get direct Ksp times K step. Sometimes they will arrange in a way that you need to invert the value. Yeah, you just need to play around with these equations. Yeah, and then you need to play around and then make sure you get this equation. Yeah, so this one is not the first time that they have asked. Okay, they have asked this many times already before. Yeah, so that is going to be how to do. Yeah, it's not a known equation. Yeah, what is known? Okay, solubility product and then stability constant. The how to write, that is known. Yeah, that one you need to know also. Yeah, you need to know. And then how to write the equations, you should know. Yeah, but there is no particular product equation that you need to memorize. Yeah, now so the next question over here is going to be the numerical value for the stability constant. Now do remember, stability constant is going to tell us about okay, how stable is the complex. Yeah, so we know that now. Okay, this particular complex, okay, the AgS2O3, the complex is given, the stability constant is 2.9. Yeah, so now okay, they say that they put the Ag plus, okay, added to solution containing equal amount of this. Yeah, so this, all these are going to be your ligand. Yeah, so they say which all these are left to reach equilibrium, and then now they are asking, this is all the complexes. Yeah, or so what we need to do is, okay, if you want to find out the highest concentration of complex, it means that we need to find out which one is more stable. The more stable it is, then the concentration of that compound will be greater. So you need to look at the data. The data over here is telling this is to the power of 18, more stable. Yeah, so AgCN2 is going to be, you are going to see this at higher concentration. Yeah, so when you explain, you just need to explain, okay, the value of the K step. Yeah, the K step, okay, value, okay, is higher, okay, for AgCN2 minus, okay, compared to, okay, these two. Yeah, so later you explain. Okay, so it tells you, okay, it means the complex is more stable. Okay, it's more stable and will be formed easily. And will be formed easily. Okay, if you compare, the second one is going to be the 13, yeah, to the power of 13. So that is going to be AgS2O3 to the power of 2, then 3 minus. And then the last one is going to be AgNH3 to H plus. So sometimes they will ask you, yeah, among all these ligand, yeah, which one is going to be a better ligand, or something like that. So a better ligand, you can actually, if they ask you to rate, yeah, the efficiency of the ligand, yeah, the efficiency of the ligand will follow, okay, the Cn, okay, is going to be more efficient than S2O3 2 minus, and S2O3 is more efficient than ammonia. Yeah, so this is how the K step, okay, give us an idea, yeah, on the stability. Yeah, so let's continue. Now, number 4, define the term lattice energy. Okay, lattice energy is going to be the energy change, okay, or no, you can say energy that is being released, because lattice energy is always going to be energy release. Okay, when 1 mole of ionic compound, okay, 1 mole of ionic compound is formed, okay, from its gaseous ion. Very important. Yeah, gaseous ions under standard condition. Okay, so if you want to write down, okay, no need to write example, but if you want to understand more, let's say, for example, you are talking about sodium chloride, yeah, sodium chloride solid is formed, okay, 1 mole of this, okay, is formed from the sodium ion gas, okay, plus, okay, Cl minus gas, okay, so that is going to be the definition for lattice energy. Okay, use the following data to calculate the value of enthalpy change of solution. Yeah, so solution, lattice energy, and hydration. You should know. Yeah, let the soul go and hide. If you follow what I taught you. Yeah, let your soul. Okay, so let your soul go. Yeah, and hide. Yeah, so this one. Or you want to memorize. Okay, hydration. Okay, equals to lattice energy plus solution. Also can, yeah, so up to you which one you want to memorize. Is still the same, okay, but in this case, okay, they say you may find it useful to construct an energy cycle. Yeah, this one I will not even use the formula, okay, because I know that hydration, yeah, hydration will come over here. It's always negative. Yeah, lattice energy is always going to be negative as well. Yeah, left and right. And then we know that either the solution, yeah, enthalpy of solution can be either positive, it can be negative, depending on the condition. Yeah, so how to calculate? First, okay, with whatever value that I have over here, normally lattice energy will come here, hydration will come here. So I can calculate the hydration first. Okay, hydration is going to be CuCl2. Yeah, so some students will forget to times 2 over here because Cu2 plus and 2Cl minus. Yeah, so they forget to times by 2. So don't make that same mistake over there. So you need to times that by 2. Okay, so if you add, okay, this one negative 378, you times by 2. Okay, it's going to be 16, 14, 15. Okay, 7, 5, 6. Okay, negative 756. And this one is going to be 2099. Okay, if I add these two, okay, it's going to be 2855, negative 2855. Okay, that is going to be for my hydration. So let's actually look at the lattice energy. Lattice energy is going to be negative 2824. Okay, normally these two values must be the same. Yeah, so here, okay, the one that is missing over here is the difference. You see 2824 is up to here only, and then 2855 is going to be all the way down. Okay, it's bigger value. Yeah, so the one that is missing over here is this one. Okay, so this value must go down, yeah, in order to make it same as this. Yeah, so therefore I know my solution, okay, is going to be negative, not positive. Yeah, so it's going to be negative. Okay, so to find this value is quite simple. Okay, 2855. Okay, you just need to minus with 2824. Find the difference. Yeah, if you find the difference, you will get the value as 31. Yeah, and that 31 is going to be negative 31. Please remember that. Yeah, so not positive 31. Okay, and if you recall what we have learned, okay, solution, if enthalpy of solution is negative value, then they are able to dissolve. Yeah, they are soluble. Yeah, or small positive, they are soluble. Okay, so this one is important. Yeah, how to calculate? Yes, this is the way to calculate. Or you want to use the formula, go ahead. I'm not going to stop you. Okay, but drawing this is much more easier to do. Yeah. Now the next question is the enthalpy change of hydration. Okay, is given. Okay, and then they ask you to use your data booklet. Yeah, to find why there is a big difference between the hydration of calcium 2 plus and copper 2 plus. Now you just need to look at the data booklet and you will know that the data booklet, okay, will tell you, okay, I didn't take the value, but you will find out that the copper 2 plus, okay, the ionic radius is smaller, okay, than Ca2 plus. Yeah, you can refer to the data booklet. Okay, if that ionic radius is smaller, okay, what happens? Okay, they are going to have a strong attraction. Okay, hydration means they are going to be the Cu2 plus in form of gas. They are going to react with water. Yeah, so it means they are going to have aqueous condition. So the aqueous over here, okay, they are going to form a strong attraction between the water molecules. Yeah, the more smaller it is, charge density is more. Okay, so you can just explain, okay, the hydration is different, okay, because the Cu2 plus, okay, has smaller ionic radius, okay, ionic radius that makes, okay, that makes stronger attraction towards the water molecules. Okay, so okay, they are going to have, okay, the hydration, okay, is going to be, this is always going to be forming bonds, yeah, so forming bonds is always negative, so this will cause, okay, the E value, the hydration, okay, to be more negative, yeah, more negative. So you can see here, okay, Cu2 plus is smaller, okay, higher charge density, okay, it attracts the water molecule stronger. So as long you mention that, we are good already. Now, the next part is going to be the electrolysis of saturated CaCl2. If you talk about saturated electrolyte, okay, so we know electrolyte, okay, they have Ca2 plus, okay, with water, then they have H plus. Cl minus with water, they have OH minus. Yeah. So in your IGCSE, and then you should know that, okay, when you have this ion, okay, they are going to be selectively discharged. Yeah. So especially when you have a saturated solution, okay, we need to focus on the anions. If it is saturated, okay, we are not normally OH minus is always being selected. Yeah, doesn't matter like any kind of electrolyte, OH is selected. But if it is saturated, okay, the Cl minus, yeah, whatever solution that you use, that will be selected. Yeah, you no need to even look at the E value. Yeah, so Cl minus will be selected. So if Cl minus is selected, okay, they are going to give you Cl2 because Cl minus, okay, will lose the electron. Okay, they are going to give you Cl2 plus 2 electrons. So this is going to happen. Yeah, so Cl2 is going to be formed at anode. Okay, but here you need to check. Yeah, even though they say saturated, you still need to check the E value, okay, between calcium and H plus. If you look at calcium, yeah, you in your data booklet is negative, okay, the E value, yeah, Ca2 plus 2 electron to give you calcium, it's negative 2.87, yeah, because it's negative. Okay, for hydrogen, no need to, I think, you know, everyone should know this, yeah, so it will give you 0.00. So we know that, okay, the one that hydrogen, okay, is 0, yeah. If it is 0, 0 is more positive than negative 2.87. So they are going to produce, okay, this is going to be more, okay, selected, yeah, compared to calcium ion. Okay, so you are going to get hydrogen gas. Yeah, so that is how we get Cl2, how we get hydrogen gas. Okay, but under normal situation, okay, at the anode, normally you are going to get the OH is going to be discharged. So we are going to get oxygen. Yeah, this one you can go and read IGCSE textbooks. Okay, you can actually get more idea if you don't understand about this. Yeah, now the next question over here is the calcium can be produced, okay, by the electrolysis of molten calcium chloride. Okay, so another mistake that students will do, or they say calcium is produced, they go and put the calcium over there. So don't go and put calcium over there because they say calcium is going to be produced. So in this case, okay, they say calcium is produced, but it's not going to be calcium. Yeah, so please take note of that. So this one is going to be simple question, straightforward question. They want you to calculate the mass of in gram, okay, 0.75 ampere pass through. So this one, okay, you just need to find out, okay, using Q equals to IT. Okay, so I'll just make it bigger here. Okay, now you just need to calculate, okay, Q equals to IT. Okay, so this one is going to be 0.75. Okay, and then the time is 60 minutes, you change it to seconds, you will get these particular columns. Yeah, so 2700. Yeah, and we know, okay, calcium 2 plus 2 electron, then only we get calcium. So 2 electron. Yeah, so 2 Faraday is going to form 1 mole of calcium, which is 1 mole of calcium is 40.1 gram. Yeah. So if you put that, okay, 1 Faraday, you can get it from your data booklet. Okay, 1 Faraday is 96500 coulombs. Okay, so it means that, okay, you want 2 Faraday. 2 Faraday is going to give you 40.1 gram. Yeah, and then I can calculate for 1 coulombs. Okay, it's going to be 40.1 gram divided by this 2 times 500. Okay, that is going to be for 1 coulomb. So I have, okay, 2,700 coulombs. Yeah, so I just need to take this value, I times by 2,700. So I times by 2,700. Okay, you will get the mass of calcium 0.561. Okay, answer in 3 significant figures. Yeah, so 0.561 gram. Yeah, so please take note. Okay, they want in gram. Yeah, please don't make the mistake. Don't leave the answer in moles. Yeah. Now the next question. Okay, explain what is meant by the entropy of the system. Okay, entropy is going to be a measure of disorder. Yeah, so it's actually a measure of disorder of the system. Okay, just like that is already enough. Okay, and then place 1 tick of each row to show the sign of the entropy change. Dissolving, yeah, when they are dissolving, they are going to become more disordered. So more disordered, positive. Yeah, water solidifying to ice, it means liquid to become solid. So they are going to become more ordered. Okay, if it is more ordered, then it's going to be negative. Yeah, quite simple. Now, the evaporation of 1 mole of water has standard gives free energy of positive 8.6. Yeah. So this one is going to be water H2O, okay, liquid, and then trying to change into H2O gas. And then they want you to sketch a graph to show how the Gibbs energy for this process between 25 degrees Celsius to 150 degrees Celsius. Now, do remember, okay, this one is going to be liquid to gas. We know the delta H is going to be positive. It's an endothermic reaction, yeah? So liquid to gas. And we know that, okay, from liquid to gas, there is going to be entropy increase. So this one is delta S is going to be positive also. And I told you, okay, they are, if you put in quadrants, last time I told you, if you have positive and negative, it's easier to determine. Yeah, but if you have the same value, the same magnitude, the positive, the same symbol, then you need to, you can actually predict, okay, which is going to be, if you just put over here, okay, imagine this is going to be liquid to change into gas, okay. This particular reaction, okay, is going to be more spontaneous at higher temperature, which is going to be closer to 100. So temperature is high, okay, then the reaction is spontaneous. So this one you should know. Yeah, I already told you. But if you do not know, you still confused, then you have to use Mr. Gopi is not so hot. Okay, that is last time I told you. Yeah, if you want to memorize this, okay, the formula. Okay, so T delta S. Okay, we know that this is a positive value. Okay, and we know that this particular thing is positive value. So if this is increasing, okay, what happens? This entire value is more positive. Okay, if that value is more positive, okay, so there is going to be chances that Gibbs free energy is going to become lower and lower, and it's going to become more negative. So it is more spontaneous at as higher temperature. So in this case, how do I apply that? Yeah, we know that at 100 degrees Celsius, okay, all water will become gas. Okay, so the moment it reaches 100, okay, there is no reason that Gibbs free energy must be positive. Yeah, so everything will be negative. So if you're not sure also where it will cross, yeah, 100, it will cross over there. So if this one is going to be at 25, is positive 8.6, yeah, the value, okay, it's supposed to decrease, and from now, okay, they will start to become more spontaneous. So you just draw like this. Okay, so this is going to be, okay, if you want to erase a little bit also can, okay, up to 150, so also can. Okay, so you just put like this, okay, straight line, okay, but must pass through 100. Okay, so the Gibbs free energy is getting more negative, it's decreasing. Yeah, now, so the reaction between A and B is feasible at low temperatures, yeah, and not feasible at high temperature. Yeah, so we want to find out. So you see just now, okay, we know that the temperature is high, okay, then the reaction is feasible. Okay, so this one is going to be positive and positive. Yeah, but now, okay, we need to find out, okay, this reaction is feasible at low temperature but not at high temperature. So we need to okay, we can apply what we have over here, okay, which is going to be the H, okay, and the S. Okay, you can actually put, okay, this one, okay, if you have delta H and delta S, positive positive, okay, sorry, positive negative, positive negative, and delta H, delta S, positive negative, this is much more easier to predict. Yeah, but the one that is going to be same is going to be difficult to predict, and it is dependent on the temperature. So this might be, if you memorize that, this will be related to that, which is going to be, they might have the same magnitude, the same symbol, yeah, the same either maybe positive positive or negative negative. Let's try. Yeah, so let's say my delta H, okay, just now temperature high, that is positive positive. So let's say I'm going to put negative over here, delta S is going to be negative. Let's see, okay, what type of reaction is negative. Yeah, so it's going to be maybe water, okay, in terms of liquid, you want to change water in terms of solid. This is going to be delta H is negative. Yeah, and then, okay, we know also liquid to change into solid is going to be negative because, okay, it's going to become more ordered. Okay, and we know at what condition this will happen. Okay, this condition will happen, okay, at temperature which is quite low. Yeah, because less than 0 only, yeah, they are going to actually change spontaneously from liquid to become solid. So I know, okay, this is going to be, we are talking about this condition. So if you know that, it's going to be easier, okay, to answer this kind of question. Okay, because, okay, the answer is going to be simply by writing it down as, okay, negative and negative, because I know, yeah, this is we learned already using the quadrant. The sign, okay, must be negative. Okay, the sign of this must be negative. Yeah, and then, okay, you need to tell why feasibility changes with temperature. Okay, so in this case, okay, you just use this Gibbs free energy. Okay, delta H, okay, minus T delta S. Okay, if it is negative, this is negative value. Okay, if this is negative, then this is going to be negative. Negative is positive. Okay, so this one is going to be positive value if the temperature goes down. Yeah, so it means that, okay, this value, the T delta S, is going to become less. Okay, so if you add, okay, if you add delta H negative with a small value, okay, which is going to go down, it means it's going to be more spontaneous. Gibbs free energy is going to be still going to maintain the negative value, yeah, as the temperature going to as the temperature is going to be going down. Yeah, so that is going to be the explanation. Okay, the Gibbs free energy, okay, is going to be, okay, going to be negative as, okay, temperature decreases, because, okay, this one negative and negative is positive, so you can say T delta S, okay, is going to be, okay, or you can say negative T delta S, okay, is going to become smaller. Okay, negative is positive. Okay, so smaller. So smaller. Gets smaller. Okay, you can just mention that. Okay, so you can see, okay, how they actually write down over here. Okay, so at lower temperature, because I mentioned about lower temperature. So at lower temperature, okay, delta H is more negative than delta T of this. Okay, so this one is going to be smaller. Okay, and then delta H is going to be more negative. Because of that, Gibbs free energy is more negative. So it depends on how you are going to explain. Okay, make sure you explain properly and get the mark. Yeah. So next question, number 5. Okay, describe okay, and explain the relative basicity of phenylamine, ethylamine, and 4-nitrophenylamine. Now, at the moment you see basicity, basicity depends, okay, on the availability, on the availability of the lone pair, from nitrogen to form dative bond to proton, or with proton. So in this case, if you look at the phenylamine, ethylamine, and nitrophenylamine, so now we compare phenylamine and ethylamine. Ethylamine, this is going to be ethylamine. They are going to have what we call as positive inductive effect. So the R group, the R group in ethylamine, will have positive inductive effect because it's electron donating group. So electron donating. So because of that, the electron pair, the lone pair of electron, is repelled, and more available for bonding. So that is going to be the first one. Then now, the most basic is going to be ethylamine. So therefore, ethylamine. Now let's actually talk about phenylamine and nitrophenylamine. For phenylamine, phenylamine, you are going to have the lone pair of electron. They are going to enter the benzene ring, and they are going to be get delocalized, with the benzene ring and become more stable. Or you can say the lone pair of electron, they overlap with the p orbitals of the benzene ring, and then they are not available for bonding. So that's one. And then the 4-nitrophenylamine, if you have this 4-nitrophenylamine, the overlapping is going to be greater because this NO2, is going to be, they are going to be electron withdrawing. NO2 is an electron withdrawing group. So when they withdraw the electron, the overlapping is going to be greater. So you can just mention about the overlapping will be greater because NO2 is going to be electron withdrawing. So the least basic, is the one that with NO2. So 4-nitrophenylamine. And then this one is going to be phenylamine. So when you explain, so for phenylamine, what you explain, so you explain about the electron become delocalized, delocalized in the pi bonding into pi system in the benzene ring. And then, for 4-nitrophenylamine, you just tell, that this NO2 group is electron withdrawing, delocalization, or the overlap, is going to be more. And less available. Just explain accordingly. So if you look at there, they would have explained everything. But do remember the important points I already mentioned. Positive inductive effect. So you see positive inductive effect. And then they tell, the lone pair is delocalized into the ring. And then this one is going to be more less basic because electron withdrawing. That's why I told you electron withdrawing. And then less able to accept the electron. So just need to make sure that you mention all this. Now the next part, they say this di-R can be synthesized from 4-dinitrophenylamine. So how do you do this? So this one is quite simple. Diazotization reaction. So what we do, the step one, is going to be you need to change this compound, into the the benzene diazonium ion. Yeah, so you need to change into that. In order to do that, okay, you need to react, okay, with this HNO2. Okay, so how do you react with HNO2? HNO2 is prepared, okay, by NaNO2, okay, with HCl, okay, where you are going to get HNO2 and NaCl. Yeah, then only you are going to get the salt. Yeah, so this reaction must be prepared at 5 degrees Celsius, because if you don't do that, then the HNO2, okay, and then the NaNO2 or the salt, okay, they are going to change, okay, into decompose into nitrogen gas. Yeah, we don't want that to happen. Okay, so anyways, okay, if you do that, okay, you are going to get this compound. Okay, you will get this compound. Okay, the NH2 will change into that. And then the next step, okay, is going to be where you are going to react, okay, with this compound. Okay, so this one, okay, this compound, okay, we have already learned about this. This is called naphthol. Okay, 1-naphthol. Yeah, so they react with this 1-naphthol. Okay, where, okay, under what condition they react? Okay, they must react with the presence of NaOH, okay, in alkaline condition, and then you are going to get that compound, yeah, which is going to be the azodine. So here, okay, they ask you to draw the structure of Q. I already draw the structure of Q, and then suggest region and conditions for step number 1 and number 2. Okay, so region, okay, I already told you NaNO2 and, okay, concentrated HCl, okay, under 5 degrees Celsius. Okay, so here, okay, they mentioned that you use less than 10 degrees Celsius. Yeah, so 5 degrees Celsius is good. Yeah, so the next step number 2, okay, you react, okay, with this compound, okay, naphthol, okay, or 1-naphthol. Okay, I will just bring it here. Okay, with this compound, okay, this is the region, and then, okay, you react with alkaline, okay, sodium hydroxide. Sodium hydroxide is already alkaline, so you react under that condition, you are going to get the azodine. Yeah, that. Okay, so do remember, okay, please go and revise about this naphthol. Yeah, naphthol, okay, if you have 1-naphthol, okay, 1-naphthol, they can react with all this. Okay, so do remember naphthol, okay, this has been added in your new syllabus. Okay, so they are going to 1-naphthol is going to activate position 2, 4, 6. Okay, but here position 2 available, okay, position 4 available, but there is no position number 6, so no need. Okay, but the thing, let's say whatever that you want to put, let's say Br, then Br will come over there. But if 2-naphthol, okay, 2-naphthol, this is number 2, okay, they are going to also activate position 2, 4, 6, but position 2 is taken by OH. Yeah, so you are left with position 4 and 6. So this is 3, 4, but they will not come over here because they say it's too cluttered. Yeah, this one I already explained to you. Okay, they, instead of going there, okay, number 6 is definitely not available. Yeah, not available. Instead of going at 4, they are going to go at this particular position. Okay, between OH and this. Yeah, so they are going to go to this position. Okay, which is position number 1. Yeah, and then the Br will go there. Yeah, you just go and revise on this part. Okay, new addition to your syllabus. Okay, now let's continue. Compound G can be synthesized from methylbenzene, okay, in 3 steps. Okay, this one, this question is quite popular, okay, because, okay, you need to be very careful which one to add or which one to convert first. Yeah. So here, okay, the final step, I see that CH3 now becomes CO2H, benzoic acid. So benzoic acid is going to be, do remember benzoic acid is going to be the methyl benzene is going to be oxidized. Yeah, so I know about that. Okay, and then you have the NO2. Yeah, NO2 is coming into position number 2. Yeah, so be careful. Don't go and oxidize the compound to this, because once you oxidize, NO2 will not come at this position, because this is going to be electron withdrawing group. They will actually put them at position 3 and 5. Okay, so they are not going to be that. So it means you still maintain CH3 first. Yeah, before it means you put the NO2 while it is still methyl benzene. Yeah, that is going to be very important. And then you can also see that Br is coming over here. Okay, and it's you can see that when you react with Br also, don't change, okay, to CO benzoic acid. Yeah, because still, okay, this is going to be depending on NO2. You see position 1, 2, 3. So it means after you change into nitro, okay, the CH3 is there, then you put the Br, then after that only the final step, only you put the acid in. It means you oxidize. This is very, very important. Yeah, so here, okay, the first step, okay, I told you, don't go and oxidize. Okay, you can either, okay, you react with this nitration. Okay, you can actually put nitration, okay, which is going to be, you react with HNO3, okay, with H2SO4 concentrated, both of them concentrated 55 degrees Celsius. Okay, and then, okay, the CH3 will come over here, NO2, okay, is going to come at position over here. Okay, so 246 directing. So you put the NO2 over there. And once you have that, okay, you are going to react, okay, you put the Br now. Yeah, don't go and put the benzoic acid. So you put the Br, okay, if you want to put the Br, so of course, you need to have Br2, and then you must have the Al Br3, okay. So because you are going to put into the benzene ring. So the CH3 will be there and O2 will be there. Br will come over here. Finally, okay, is the part that you put the oxidation. But the oxidation, also be careful. Yeah, oxidation in this case must be alkaline, okay, KMnO4, and then acidified. So slightly different. And then, of course, you need to heat them up. Yeah, so here, okay, give the systematic name of compound G. Okay, compound G is benzoic acid. Yeah, so this is benzoic acid. Okay, so benzoic acid. Okay, so automatically this is position number 1. This is position number 2. This is 3, 4. Okay, you see 2 nitro, and then you have 4 bromo. Okay, and then benzoic acid. So which one comes first? Follow alphabetical order. Do not follow the number. Yeah, so students always make that mistake. B comes first. Okay, so 4 bromo, 2 nitro, benzoic acid. Okay, done. Okay, deduce the identity of E and F and draw. I already draw. Suggest the reagents and condition for each step 1, 2, 3. Okay, so the reagent, okay, concentrated, you write in full. Yeah, concentrated nitric acid. Okay, concentrated H2SO4. Okay, and then the condition 55 degrees Celsius. Okay, step number 2, you use the Br2. Okay, and then and AlBr3. Okay, and then step number 3, okay, alkaline, KMnO4, and then acidify. Okay, then heat. Okay, heat. Okay, you can check. Okay, the marking key, concentrated. I think they forgot to put the 55 degrees Celsius. Okay, this is okay. Hot. Yeah, okay. Okay. Yeah. So now, next question number 6. There are 4 possible isomers of C8H10, okay, that contains benzene ring. So it has a benzene ring. Yeah. So it means all of them, okay, they will have a benzene ring. So I will just draw. And then, okay, they say that, okay, if you observe using carbon-13 and a mass spectrum, they are going to have certain peak. Yeah. So here, okay, I have C8. Okay, C8. Now I have C6. So there are two carbons. Okay, there are two extra carbons over there. So what I can see, the moment I have two extra carbons over here, I will think, okay, maybe there is a benzene. Okay, maybe two carbon, maybe C2H5. Okay, let's check whether it's correct or not. Okay, I'll just put C6H5. Okay, and then C2H5. Let's see, C8H10. So you see, compare. Okay, correct. Yeah. So let's actually look at the number of, okay, if I use this, let's find out what is going to be the what is going to be the number of peaks, yeah, of the carbon. Okay. So if I look over here, okay, if I just put the CH2, CH3 here, okay, I know that, okay, this is going to be 1, okay. So this is going to be another 1, so 2. Okay, this carbon is going to be different, so number 3. Okay, do remember last time I told you, if it is like this, then put something like this. Okay, so this carbon and this carbon, okay, I fold, is symmetrical, so it's going to be the same. Yeah, 4. This carbon and this carbon, if I fold, it's going to be symmetrical, so it's 5. This is different, 6. So they have 6 peaks. So let's see which one has 6 peaks over here. 6 peaks over here. Okay. So when I draw, okay, so you just need to maybe I'll change this a bit. Okay, I'll put it this way. And then I put, okay, this one carbon here. Okay, another carbon over here. Okay. So, or I can actually put it 1 carbon here, another carbon over here. Okay, so this is going to tell that this is going to be 1 carbon, another carbon. So this is going to be 6 peaks. Okay, now other isomers that I can think of, okay, instead of putting that way, okay, they say structure isomer. So maybe I'll just start to put 1 CH3, okay, and then I put another CH3 here. Okay, this one, if I want to check also, you can check. C6H, 1H is gone, 1H is gone, C6H4, CH3, CH3. Let's see. Okay, C8, okay, 7, 10. Okay, 7H10. Okay, so same. Okay, so can be used. Okay, but okay, do remember, let's find out how many peaks. Okay, this one, I will draw the symmetrical line over here. Okay, and okay, or okay, you can also draw the symmetrical line over here. No harm. Yeah, so let's actually draw that. Okay, ignore this. Okay, when I do that, okay, this is going to be 1. Okay, this is also 1, the same. Okay, the same peak. Okay, and then I know that this is going to be 2, and this is also 2. Same. Okay, they're symmetrical. Okay, and then, okay, because symmetrical, this is going to be the same as this 3. Okay, now because they are symmetrical over here, okay, this one is the same as this. Okay, you can see 3 and also 3. Okay, why? Because they are attached to CH3. This is going to be attached to CH3. They are the same. So they are total how many carbon environment? 3 carbon environment. So if it is 3 carbon environment, 3 peaks. So this one, 1 here, 1 here, done. Okay, I'm done with isomer 1, isomer 4. Okay, let's look at isomer 2 and 3. Okay, what else I can do with this? Okay, I can actually put, okay, the CH3 here. Okay, and I put the CH3 here, side by side. Okay, let's check. Okay, side by side. Okay, if I check side by side, okay, how to look at it? Okay, so let's say I'm going to put a symmetrical line over here, and then I know that this is the same as this carbon. This is going to be the same as this carbon. This carbon is the same as this carbon. This carbon is the same as this carbon. Okay, so 4 environment. Okay, 4 environment. So if you have 4 environment, okay, 4 peaks, let's actually go and look for 4 peaks over here. Okay, so 4 peaks is going to be this one. Yeah, so side by side. So 1 here, 1 here. Done. Okay, so the last one is going to be 5 peaks. Okay, so let me check. Yes, I already put, okay, side by side at position 1 and 2. Okay, I already put like this. I already put 1 and 6. The only thing that I didn't put yet is going to be this position. So I put the CH3 here and CH3 here. Okay, let's try this. Okay, so I put the symmetrical line over here. Okay, and I know this is carbon number 1. This is carbon number 2, the same as this. This is carbon number 3, this one, yeah, the same as this. This is going to be carbon number 4, the same as this. Carbon number 5, 5 peaks. Check, 5 peaks, yes. Okay, so 1 here and another 1 here. Done. Okay, this is how you solve this question. Yeah, so make sure. Okay, I think most of the students will get confused with the 3 peaks. Yeah, the 3 peaks. Okay, you need to remember the 3 peaks is going to be this, this, and this, and this. They are the same. Yeah, that is the most common mistake students will make. Okay, let's move on. Okay, a 3-step synthesis, okay, of X, okay, from benzene is shown. Okay, so when you look at here, okay, they have shown you, okay, step number 1. Okay, the moment you see AlCl3 over there, okay, this is going to tell you that they are going to go and replace the hydrogen directly into the benzene ring. Yeah, so you are going to bring, okay, this compound into the benzene ring. Okay, but there is Cl there. Okay, and we know that the moment there is Cl, it can be Friedel-Crafts acylation and Friedel-Crafts alkylation. So what type of reaction is this? This is going to be Friedel-Crafts alkylation. Yeah, why? Because this is going to be carboxylic acid. So the carboxylic acid will stay there. Okay, the Cl is the one that is going to go out. Yeah, so with the H over there, so they will come over here. So you see here there are 3 carbon, 4 carbon. So 1 carbon, 2 carbon, 3 carbon, 4 carbon. So I just draw. Yeah, so the one that is going to go out is HCl. Okay, this is W. And then, okay, the moment I have this O, okay, I know the OH is going to change into Cl. Okay, so how the OH, the carboxylic acid can actually go into getting something into Sl chloride? There are 3 regions that you can use. Okay, you can use PCl5, SOCl2, PCl3. Yeah, if you are using that, you need to know the condition. PCl5 is room temperature. SOCl2 is room temperature, but it's not popular because they give you harmful gas, SO2 and HCl. Yeah, PCl5 is more safer. Yeah, so they tend to use that. PCl3 not so popular because you need to heat them. So you need to provide heat. Yeah, so PCl5 is more popular. Okay, so once you do that, you are going to get the Cl over there. Okay, and then the last step is the one that every students will get confused how to do. Yeah, so this one, okay, the moment you see, okay, when I calculate this, okay, I am going to have, okay, C10H11OCl. This is going to be C10H11OCl. And then I know that the moment I have a halogen carrier, it is going into my benzene ring. Yeah, I'm not adding anything else. And then suddenly I notice the hydrogen from 11 changing into 10. It means that it is something to do with this compound is directly, okay, going into the benzene ring. So what happens, okay, is going to be this Cl, okay, they are going to actually come over here, okay. So they are going to react maybe either because generally it's supposed to be this position. Yeah, they are going to actually react with this H. Okay, they are going to remove H and Cl. This particular bond will form at this position. Okay, so if I draw that, okay, and show you, okay, so there is 1, 2, 3, 4 carbon. So if I draw maybe 1, okay, 2. So 1, 2, so 3, okay, and then there should be fourth carbon. Okay, 4 carbon. Yes, so sorry. So 4 carbon, 1, 2, 3, 4 carbon. Okay, let me draw again. So 1, 2, 1, 2, 3, 4. Okay, then this fourth carbon, they will join over here. Okay, so the fourth carbon has oxygen. Okay, and they are going to give you, okay, HCl. This is something that you need to is unique. Yeah, it's unique. They do accept, okay, instead of going to this position, if you put at this position, that is also accepted. So you see here, okay, if you just go and put into that position also, it's accepted. Okay, so please take note. Okay, so I went and draw this. Yeah, I went and draw this. Okay, so up to you which one you want to draw. Okay, but the best answer is going to be this one. Yeah. Now, step 1 is the alkylation of benzene by electrophilic substitution. Okay, use the RCl to represent this. Okay, so write the equation for the formation. So basically RCl, okay, plus AlCl3, they are going to give you AlCl4 minus, okay, plus R plus. Okay, so this is going to be what you are going to get. Okay, so deduce and draw the structure of W and X. I already draw. Yeah, suggest the region and conditions for step number 2. Yeah, which step is that? Step number 2. Yeah, this one I already told you. If you use PCl5, so PCl5. Okay, condition room temperature. Next. Now complete the mechanism for the reaction with the electrophile form in B1. If you do not know which one is electrophile, then it's a problem. Okay, the electrophile is something that is going to be attracted towards electrons, so R plus. Yeah, so you can just use the R plus. No need to use the full version. Yeah, so here, okay, what happens? Okay, we know here the product is going to this position. Okay, so make sure, okay, the electron is going from here to there. Okay, hold on. It's a curly arrow, so you must draw a curve. Yeah. So make sure the arrow is from the electrons. Okay, from the electron, it shows the movement of electron. So when it goes over there, okay, you are going to have, okay, this structure. So do remember the U must be slightly to here. Okay, and then you will have R. You have H. Okay, why the H must be shown? Because you are going to draw the electron from here. The 2 electrons will come over here again. Okay, and then you will get that. Okay, if you want to include plus H plus also can. Yeah. Now, anyway, okay, all the charges, curly arrow, everything is included over there. Okay, to show the movement of electron pairs. Yeah, you will get the 3 marks. Now, the next question. Okay, what is order of reaction? Yeah, to save time, okay, I already put down over there. So the order of the reaction, there is no specific definition. Yeah, so you just need to use the rate equation. Rate equals to, okay, let's say the reactant, okay, to the power of, okay, K to the power of, let's say, whatever value A, B, C. Yeah, so this is the order of the reaction. So what is order of the reaction? The power, okay, to which the concentration of the reactant is raised in the rate equation. Okay, you can include, okay, this is determined by experiment. Yeah, here I think the answer, they just say power. Yeah, so better, okay, if you can include, okay, this one is determined by experiment. Okay, now use the data, okay, to determine the order of the reaction. Now this data, if you want to use, quite simple. Yeah, like how you have done before. Okay, so for now, let's say, for example, I use the experiment 1 and 2. Yeah, experiment 1 and 2, this is constant. Okay, if this is constant, I can see when I times by 4, okay, this one, when I calculate, okay, this value, I also get the value times by 4. If the number is the same, okay, this is going to be first order reaction. So I know that, okay, you explain, yeah, you explain using this, and then I know that this is going to be first order. Okay, that is the first one. And then the second part is going to be, you need to make sure the other OH is constant. So I use this. This is constant. Okay, so I will use experiment number 1 and number 3. So when I do that, okay, you can see from here to here, okay, from 0.20 to become 0.50, okay, I times 2.5. Yeah. So when I times by 2.5, what is the value from here to here? Yeah, I will get a value which is 6.25. Okay, what does it mean? Yeah, so I just check whether is it going to be second order or not. Yeah, so I just, what I do, 2.5 times 2.5, I will get, okay, 6.25. So I know, okay, 6.25 is actually 2.5. Okay, 2.5. Is it 2.5? Okay, 2.5 to the power of 2. Okay, so 2.5 to the power of 2 is going to be 6.25. Therefore, we are looking into second order reaction. With respect to what? With respect to ClO2. So I'll get this. So you please use the data and explain. Okay, you explain and you will get the 2 marks. So make sure you show this experiment, show the value and so on. Okay, and you explain accordingly. Use your answer to construct the rate equation for this reaction. So you just put K. Don't forget the K. Yeah? So K, and then you put the OH. 1, no need to put 1. So ClO2 to the power of 2. Okay, you just put over there. Okay, once you have that, okay, you just move on. Use the rate equation and the data in experiment 1. So you use the data from experiment 1 to find the value of K. So rate, okay, in experiment 1 is 7.2 times 10 negative 4. Okay, 7.2 times 10 negative 4, okay, equals to K. Concentration of OH is going to be 0.03, okay, 0.03. And then concentration of ClO2 is 0.02. And don't forget to the power of 2. You calculate the K. Okay, the K is going to be 7.2 times 10 negative 4. Okay, this is going to be rate. So it's going to be mole per dm cube, okay, per second. Okay, and then you divide, okay, with 0.03, and then you divide with 0.02 to the power of 2, which is going to be mole to the power of 3 dm, okay, to the power of 9. Yeah, so you calculate, okay, you will get the K value. If you calculate the K value, you will get 60. Okay, 60. And then the unit, okay, you can see the unit over here. Okay, mole, you cancel with this, there's 2. Okay, you negative 3, you cancel, then you will get negative 6. Okay, so if you bring it up, okay, you will get mole negative 2, dm 6, from negative 6 becomes 6, and then negative 1. Okay, that is going to be, you will get that. Yeah, so that is going to be what you need to do. Okay, the K value 60. Okay, calculate accordingly. So next question, okay, question number 7. So here, okay, they say that the decomposition of the benzene diazonium salt. This one, okay, even we didn't learn about decomposition of diazonium, yeah, but you should know, yeah, which is going to be when you add water, large excess of water, okay, the product, yeah, if you have diazo salt, okay, when you react, okay, this one is related to the reaction with sodium hydroxide. Okay, when you use sodium hydroxide, okay, in alkaline condition, okay, what will happen? You are going to get the formation of, okay, phenol. Yeah, so this is going to be without the presence of sodium hydroxide, you're still going to get phenol. So this is very important. Okay, so what is going to happen? Okay, instead of getting this, okay, you are actually going to get, okay, this is going to give you phenol. Okay, the OH from here, instead of OH coming from here, the OH will come over here. Okay, they will go and enter. Okay, so you have C6H5OH. Okay, and then you have H plus. Okay, you are going to have nitrogen gas being released. Yeah, so this is going to happen. So why I'm putting over here, because they say draw the structure of organic product. Okay, the organic product that is going to be formed is phenol. Okay, OH. Must know. Yeah, must know. Now, they said over here it's going to be concentration, okay, versus time graph. Okay, do remember concentration versus time graph. Okay, if you use the rate under this chapter, okay, there are two types of graph. Yeah, one is like this. Okay, another two will be like this. Okay, they will be curved. Yeah, so this one is going to be zero order. The one that is going to be curved can be either first order or second order. How to determine first and second order? For first order, half-life is going to be constant. Yeah, so that is how you determine. So in this case, okay, this is concentration and time. Yeah, so in this case, you can see a curve. So we know it's first order or second order. Okay, but they say already it's first order. So I know that the half-life must be constant. Okay, so you have this. Okay, use the graph to determine the rate at 100. Now, to determine the rate, okay, do remember rate is going to be the gradient of concentration of time graph. Okay, so you need to show them how to get a tangent. Okay, so I will just roughly draw here. Okay, tangent. I will draw something like this. Okay, so you need to do it accurately. Okay, let's say here, if I just roughly use from here. Okay. Okay. So if I use these values, okay, from the bring it up a bit. Okay, not so good looking, yeah, but again, okay, if I put it over here, okay, I'm assuming this one is going to be 0.016, okay, and this one is going to be 0.006, okay. So this y is going to be 0.010, okay. The x, okay, I am taking it as from here, okay, which is going to be 20 all the way to here, maybe 190. Yes, so I'll take it as 190. Okay, so the difference is 170. Okay, so I show already over here. Okay, if I want to show determine the rate, okay, the rate equals to 0.010 y divided by x. Yeah, so 170. Okay, if you calculate, okay, your calculator, you can calculate. Okay, if you calculate, you will get 5.88 times 10 negative 5. Yeah. So this is my answer. Yeah. Maybe not so accurate. Okay, if I just draw using paper. Yeah. So you just calculate accordingly. Okay. Tangent. You need to draw the tangent. So I get 5.8, okay, times 10 negative 5. Yeah, so something like that. Yeah, so I will just use this. Okay, you calculate accordingly. Okay, now the next part. Okay, you are going to sketch a concentration time graph. Yeah, so if you want to sketch the concentration time graph, okay, this graph, okay, for concentration time graph, okay, I already told you, if it is going to be zero order, okay, then the graph is going to go down like that. Yeah. So this one is assuming that you are going to draw for the reactant. Yeah. So in this case, okay, the sketch the graph. Okay. So I just sketch. Okay. Follow the zero order. And then, okay, they ask you, okay, how's the successive half-life? What is half-life? Half-life is the time taken for the concentration to become half. So if I take from this value to this value, so half is going to be somewhere here. So if I just plot over here, I know that this is my half-life. So from here to here, I know the half is over here. So if I bring over here, okay, and I bring it down, I know that my half-life now is getting smaller. And then if I take from here to here, you can see also it's getting smaller and smaller. Yeah, smaller okay, keep on getting smaller and smaller. So you can say the successive half-life decreases. Okay, so the one that is no change in successive half-life is going to be for the first order reaction. Yeah, so please remember that. Yeah. Now, so the next part, okay, is going to be question number 8. State and explain the relative rate of hydrolysis. Okay, so the hydrolysis, when they say acyl chloride, so this is R acyl chloride. Hydrolysis means they are trying to break this. Yeah, and then they say alkyl chloride. Okay, alkyl chloride is RCl. Okay, they try to break this. And then aryl chlorides. Okay, this one we have already learned. Okay, this one is more difficult to be broken. Why? Because the electron go and overlap with the p orbitals, okay, in the benzene ring. Yeah, so they become delocalized over there. So it's very difficult. Okay, they will have this partial double bond character. Yeah, difficult to be broken. Okay, so in this case, they say explain the relative rate. The one that is slowest must be aryl chlorides. Okay, the one that is going to be in between is alkyl chlorides. Okay, the one fastest, okay, to be hydrolyzed is this one because of the presence of the oxygen. Okay, the oxygen, they have this negative inductive effect. Yeah, so this one I will just put there is a negative inductive effect. What is negative inductive effect? So basically they are going to be the oxygen is more electronegative. Okay, so they are going to withdraw the electron. Okay, withdraw the electron. Okay, so that, okay, they become delocalized. Okay, delocalized between carbon and O. Okay, and the C double bond O. Okay, making CCl weaker. Okay, the bond becomes weaker, so it's easy to hydrolyze. Okay, so this one RCl. Okay, RCl, you can say R is a alkyl group. Okay, so it's electron donating group. Okay, or they are going to have positive inductive effect. Okay, positive inductive effect. So the RCl is strong. Okay, the bond between RCl is strong. And then the last one, okay, you need to tell the lone pair of electron of Cl delocalized into benzene ring where the p orbitals overlap and give partial double bond character. Difficult to be broken. Yeah. So all these, okay, all these are explained over here. Yeah. So you see, you can see all the terms that I use. Okay, electron deficient, electronegative atoms. Yeah. And then as aryl chlorides, okay, they become part of the delocalized system, partially double bond character, okay, delocalized into pi ring. And then alkyl chlorides, okay, electron donating effect, positive inductive effect. Okay, all the terms that I use are there. Yeah, so please refer to the marking key. Yeah, but yeah, if you want to, okay, all the points are there. Enough, okay, to get the 3 marks. Okay, so next, okay, the drug, okay, is shown. Okay, so they say this drug is completely hydrolyzed under acidic condition. Yeah, so if you hydrolyze this drug in acidic condition, so you need to know, okay, under acidic condition, what which are the bonds that is going to be broken. Yeah, the bonds that are going to be broken, okay, you can see, okay, this bond, okay, the ester bond is going to be broken. And then we also have the amide bond. Okay, the peptide bond also going to be broken. So these are the where the bonds are going to be broken. Okay, so when I see from here, okay, I get the first thing I get is going to be this one. Okay, is CH3. Okay, so I can just write down, okay, CH3 and then O. Then this one must be H. And then this one also, when I break this, This is also CH3OH. So it's the same. No need to draw again. Yeah. So that bond, okay, is going to be, we have already known that is going to be CH3OH. Okay. Now, so this one is done. Okay. This one is also done. Okay. Let's draw the simple one first. Yeah. So this one. Okay. When I have this, so I'll draw like this. Okay. Then draw like this. Okay. This one O. Okay. This one is going to be OH. Okay. So OH will come here. Then this one will become H. Okay. So this one also OH will come over here. Okay. This one OH will come over here. Yeah. So I will draw, okay, the other one, the bigger in the bigger space over here. Okay, I'll draw, okay, OH, and then like this. I'll just try to follow what they have given. Okay, and then you have N. Then you go like this, and then I have another N. It goes like this, and then H. This one, double bond O, and then you will have OH. Okay, now this is, okay, the one that is given in your marking key. Yeah, but okay, please remember, okay, there are 3 answers for this. Okay, so I will copy and paste over here. Okay, because, okay, they have mentioned that this reaction is going to be done under acidic condition. Now, under acidic condition, okay, we have certain compounds over here, okay, which is going to be OH is acidic, so they are not going to react. Yeah, but nitrogen, okay, they have lone pair of electron under acidic condition. Okay, they are going to form, okay, the dative bond. Okay, dative bond with the hydrogen H plus. Okay, so one of the answer is going to be, okay, you can have, okay, another H over here. This is going to be positive. Okay, so there is going to be H will come over there. That will be positive. That is one of the answer. Another answer is you can still maintain this positive. Okay, there is another nitrogen here. You can bring another hydrogen here. This is going to be positive. Yeah, these are the 3 answers that are going to be accepted. Okay, that's why here, okay, let me show you. Okay, this answer is accepted. Okay, but okay, allow amine salt for the third structure, mono or di ion. Yeah, this is mono, this is di. Okay, so both also accepted. Yeah, 3. Yeah, 3 are accepted. Now, next, okay, we look at this structure. Okay, this one, okay, compound Y, okay, C5H10O2, they react with Na2CO3, okay, to evolve bubbles of gas. Yeah. So the moment, okay, when I see this, okay, there are 5 carbon compound. Okay, most probably, okay, it can be alcohol. Okay, it can be carboxylic acid. Yeah. Why alcohol? Maybe I can have 2 OH group. Yeah. Or I can have carboxylic acid C double bond O with H. I have 2 O. Yeah. So that is I decide that first. Yeah. And then, okay, the proton NMR is used, and then the compound is D2O. So it means that the bond between the hydrogen for the OH will not be shown over here. Okay, it will not be shown over here. So I need to come up, okay, with the structure, okay, that can best represent this. Okay, so when I look at this peak, I can see in total there are going to be 1 peak, 2 peak, 3 peaks. Yeah, 3 peaks, 3 hydrogen environment. Okay, if you answer like this is automatically wrong. Why? Of course, this one cannot be detected. Yeah, but you see 1 environment, 2 environment, 3 environment, 4 environment. So supposed to have 4 peaks. Okay, this one is going to be 3 peaks only. So cannot. Okay, and another one more indicator, okay, that will help us to draw this is this. Okay, you can see this is a high resolution NMR, okay, where they are going to be splitting 1, 2, 3, 4, 5, 6, 7. It means that one of the hydrogen, okay, the neighboring carbon has 6 hydrogen. Okay, so it means that the neighboring carbon must have 6 hydrogen, means something like this. That's the only way. Okay, this is how I decide that. Okay, I must have this structure. Okay, I must have this structure. Okay, so that is the first structure. Okay, that will help me. Yeah, so I must have this structure. Okay, and then I have this double duplet. Yeah, so if I look at this, maybe most probably this carbon and hydrogen environment, they have one, so possible. Yeah, so I'm just need to figure out the remaining 2 carbon, because it's going to be C5. Okay, remaining carbon, how will it look like? Yeah, so I know one doublet, so I should have another one that is possible to give me doublet. Yeah, so it means there must be CH2 like this. Okay, why? Okay, when I put the CH2 like this for this environment, okay, there is going to be one hydrogen environment here, which will give me my doublet here. Okay, so I know that roughly I will have this hydrogen here. Okay, and then finally, okay, I only have another one more carbon here. Okay, and then I cannot just put OH, okay, directly, because the moment I put OH and OH here, I will have some other environment which I don't require. Yeah, this one cannot be seen, but there is another additional environment will come over here, which is wrong. Okay, so instead of doing that, okay, that carbon, okay, I know for sure it's going to be carbon double bond OH. Okay, because you need 2 oxygen, and this one, okay, will not be detected. Okay, will not be detected by NMR spectrum because D2O is going to be used. So it matches. Yeah, so if I look at it, okay, you have one environment. Okay, all these are the same environment, one environment. So this is going to be, okay, if I draw one environment, okay, and then this is going to be another environment, and this is going to be another environment. Yeah, so you are going to have total of 3 peaks. Yeah, 3 peaks. This one will not be seen, so 3 peaks matches. Yeah, so I know this is confirm going to be this. Yeah, this is how you identify. Now, okay, use the data booklet, okay, and answer to complete the table. So now I have put the data booklet here, the information of the data booklet over here. So if I look at, okay, let me erase this first. Now, if I look at the let's look at the something that is obvious first. Yeah. So this one, okay, the one that is going to be at 1.9. Yeah, 1.9 is the one that has the splitting pattern. If you have more than, okay, you see more than quartet, more than 4, okay, doublet, okay, we have triplet, quartet. Yeah, so in this case you have 7, so we call it as multiplet. Okay, multiplet. And then, okay, the number of hydrogen atoms responsible for the peak. Yeah, do remember that is going to be the multiplet is going to be the one that is going to be the neighboring. So it means that most likely this one represents this hydrogen. Just to confirm, yeah, just to confirm. Okay, 1.9. So you just look at 1.9. Okay, 1.9. Okay, they can come somewhere here, or they can come somewhere here, but I think there is no exact answer. Okay, so you can just say it's CH. Yeah, CH, which is going to be still will come under alkene. Yeah, still under alkene. So I can just put this answer as alkene. Okay. Okay, or CH. Okay, multiplet. Number of hydrogen atoms responsible for this state, there's only one. Okay, one. And then for 0.95, okay, you see 0.95 is this one. Okay, 0.95, the neighboring must have one hydrogen. So 0.95, the neighboring must have one hydrogen. So it can be either here, neighboring one hydrogen, or it can be this one. Okay, so we don't know which one. Yeah. So in order to do that, okay, you just have to look at the data. But do remember, this hydrogen is next to carbon that contains CO. Yeah. So that is going to influence that. Yeah. So let's actually look at the value 0.95. Okay. 0.95 is just going to be a normal alkane. Okay. A normal alkane. So I'll just put alkane. A normal alkane. Okay. In this case, a normal alkane, not this one. Yeah. So must be this one. The carbon hydrogen. Okay. Next to CH3. Yeah. Or I think if you just put alkane, it's also okay already. Okay. CH. So at least like this. Okay. But the 2.2. Okay. But before we go there, okay, 0.95 is going to be doublet. And how many? Okay, responsible. Okay, so I know this one. Yeah, this is only one. Okay, sorry, alkane doublet. Okay, this one is going to be this one. Yeah, not this one. Okay, just now this is the one that is going to be 1.90. So this one. So alkane, this is going to be in the CH3. Yeah, so maybe I'll just draw CH3 like this. Okay, so how many responsible for this? You have 6. Yeah, the green 6. And then the last one, 2.20. Okay, let's look at 2.20. Yeah, you can see here. So it must be alkyl next to C double bond O. Yeah, so you just need to mention that in your answer. Alkyl next to C double bond O, which is this. Yeah. So this one, how many responsible? 2. Okay, 2. This one and this one. Okay, and then splitting pattern. Okay, you have doublet. Okay, I think that's all. Okay, done. Okay, so guys, okay, all done. Okay, any particular question? How many? I think towards the end, only 4 of us remaining. Yeah. So any question, those who are here, okay, any question that you want to ask? Or any part that you want me to go through again? Ashley, are you there? Okay. So if there is no question, roughly, let me just go through here. Okay, when I see this part, okay, let me see. Okay, maybe we'll go through this H2O2 again, yeah? Okay, maybe some of you may be still confused. Okay, I'll just, to save space, I'll just put it over here. Okay, so the H2O2, okay, H2O2, I need to use the data from the H2O2. So no, yeah, so 1B and C, yeah, and then mentally kind of. Okay, let me see, yeah, Fredo is asking for 1B and 1C, yeah, 1B and 1C. Okay, this one, yeah. Okay, this one, okay, I just refer to the marking key, yeah, because it's related to CO, yeah. Just double check again, Fredo, yeah, whether for CO, okay, when you use the OH, okay, and when you use excess ammonia, okay, because it's excess, yeah. So what will happen? Okay, just go and check again, okay, with the equation that we have, okay. But okay, I will actually teach you about the H2O2. Yeah, maybe that is the part that a lot of people confuse. Okay, so I will get the data booklet. Okay, if you have the data booklet, you can also take the data booklet. Okay, I'll try to cover that part. Okay, now for H2O2, okay, I will look at, they say H2O2. Okay, so I will just look at the data for the H2O2 from the data booklet. Okay, if you have the data booklet, you can also look at the data booklet. H2O2. Yeah, so I have this H2O2 plus 2H plus 2 electron, 2H2O, and that is going to be positive 1.77. Let me check whether there is any other H2O2. Yeah, there is no other H2O2. Yeah, so that is one. Okay, and then okay, we have the CR. Okay, CR3 plus. Okay, so you need to get everything related to CR3 plus over here. So I will try to put all the CR3 plus equation here. So you have CR3 plus electron to give me CR2 plus negative 0.41. And I have CR3 plus 3 electron to give me CR. That's going to be negative 0.74. Let me check again. Yeah, correct. And then there is another one more. Okay, CR. Let me check again. CR2072 minus plus 14H plus 6 electron to give me 2 CR plus CR3 plus 7 H2O, and that is going to be positive 1.33. Okay, so I have all this. Yeah, so okay. So Fredo, you can see, I think the question is more towards here. Yeah, so if you look over here, okay, I know that the reaction is going to be, they say, reacting with H2O2. Yeah, if it is reacting with H2O2 means this H2O2 must be moving forward. Okay, please remember this. Okay, it must be moving forward. So if that is moving forward, yeah, so I'll go very slowly over here. If that is going to be moving forward, if this is going to be positive 1.77, okay, if that is moving forward, the reaction, okay, that involves, okay, CR3 plus must be moving backwards. Okay, please remember this. Okay, it must be moving backwards. So if I look at the one that the values, yeah, the values over here, okay, negative 0.41, okay, this is more positive, this is negative. So I know, yes, it will move backward. Okay, but when it moves backwards, okay, Fredo, you can see that this is producing CR3 plus. I don't want CR3 plus because I'm reacting with CR3 plus. Okay, I eliminate the first one. And then, okay, You see, this is positive 1.77. This is negative 0.74. Of course, this is also going to go behind. But I don't want that as well. Okay, because it is producing CR3 plus. I don't want CR3 plus. I want CR2 plus. Yeah. Or I want something else. Yeah. So it means I want CR3 plus. Yeah. To react. Okay. I want it to react. So when I put over here, the last one, you see 1.77 and 1.33. They are also going to go behind. Yeah. But the good thing over here is the one after they react, this is reacting with CR3 plus, which is what we want. Okay, which is what we want. Okay, and the product that they will give you is going to be this. Okay, so that's why I use the CR2072 minus. Okay, but according to the marking key, there is another answer. Yeah, let me check also for that data. Yeah, so the answer that is given is going to be something to do with CRO something. Yeah, let me check from the data booklet. Did I miss anything else? Okay. CR3 plus, what else? From my data booklet here, yes, yeah, CR207. Yeah, I have that. From my data booklet that I'm using, it's not there. Okay, let me check the market key again. CRO4. Okay, let me check for CRO4. CRO4. For those we already finished the paper. Yeah, those who wants to go also, you can go already. CRO4. I couldn't find. Okay, maybe I'm too tired also. Yeah, it's from my data booklet. Yeah, I don't see any CR04. Yeah. Okay, but if maybe they use a different data booklet or what, you can also have the CR04. Okay, but in this case, we do in our data booklet, that the recent one, it's not there. Yeah. So because of that, I am just going to use this one as my final answer. Yeah. So what actually happens, when you combine these two, the H2O2 plus 2H plus 2 electron to give you 2 H2O, that's going to be 1.77. So this one is going to be 2 CR3 plus 7 H2O, to give me CR2O7 to minus plus 14 H plus and 6 electron. That is going to be negative 1.33. You can find the E value, if they ask. So 1.77, 1.33, so 4, yeah, 0.44 positive, yeah. And then you want to join the equation together, so this one I have to times by 3, yeah, 3, 6, 6, and then times by 3, 6. So if you join the thing together, the final answer, you will have 3H2O2 plus 6H plus 2 CR3 plus 7 H2O. The electron will be gone. 6H2O plus CR2O7 2 minus plus 14H plus. So that is the concern. How do we know which one is oxidized and which one is reduced and so on? Yeah, because you see, this is the part that receive the electron. Yeah, H2O2 is receiving the electron, so reduction. So H2O2 will undergo reduction, gain of electron. So something that undergo gain of electron. So this is the oxidizing agent. So this is going to be losing. CR3 plus is losing the electron. So CR3 plus is going to be oxidize. Okay, so oxidize, or you want to find the oxidation number also, you can find. So you see this one involves redox reaction, therefore, okay, we say redox, or yeah, they say oxidation. Yeah, so that's all. Yeah, is that clear, guys? Okay, I think that's all. Okay, if you still not sure, okay, you can always check my yeah, you can always type the comment over there. Maybe I'll try to reply when I see there. Yeah, but I think it's done. Yeah, it's done. Okay, thank you, guys. Okay, thank you for the 4 people who are still here. Okay, but good. Okay, you also get rest. Yeah, take care, guys. Okay, I'm going to end the streaming. Yeah, see you guys. Bye.